And now in this lecture we find out the area of a semicircle. In the drawing we have a quarter circle. AOB is a quarter circle. Inside this quarter circle we have this semicircle, and our mission is to find out the area of this semicircle. In addition, we also know that AO equals to 5 units in its length. That is to say, the radius of this quarter circle is equals to 5 units. So, in the first step, we will define the relevant points to this question with letters. We will define the center of this semicircle. This point is point C. We will define the touching point of this quarter circle with this semicircle. This point is point D. We will define the lower touching point of the semicircle with this quarter circle as point E. Likewise, we will define the point of tendency of tangent BO with this semicircle. This point is point F. And finally, we will define the point of tendency of tangent AO with this semicircle. This point is point G. In addition, we will define the radius of this semicircle as X. Therefore, CD is the radius of this semicircle. That is equals to X according to our definition. CE is also the radius of this semicircle, and therefore it is equals to X. In the next step, we will join point C and F together by a straight line. CF is of course the radius of this semicircle, and therefore it is equals to X according to our definition. Here we can implement rule 1 because we have the radius CF of this semicircle that is 1 to point F, that is the point of tendency of tangent BO with this semicircle. And whenever you have a radius that is 1 to the point of tendency, then tangent BO will be perpendicular to the radius FC according to rule 1. If BO is perpendicular to FC, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees. Likewise, we will join points C and G together by a straight line. CG is of course the radius of this semicircle, and therefore it is equals to X according to our definition. Again, we have the radius CG that is 1 to point G, that is the point of tendency of tangent AO with this semicircle. And whenever you have a radius that is 1 to the point of tendency, then tangent AO will be perpendicular to the radius GC. If AO is perpendicular to GC, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the same rule, rule 1. So by doing these constructions, we actually get a quadrilateral CFOG. Inside quadrilateral CFOG, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this 4 pieces angle, in total they must be equal to 360 degrees. According to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this 4 pieces angle must be equal to 90 degrees in its size. So inside quadrilateral CFOG, we have 4 right angles, and according to rule 5, any quadrilateral that has 4 right angles must be this rectangle, if not a square. So we relate to this quadrilateral CFOG as a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So rectangle CFOG, side CG must be equal to the opposite side FO. But CG is x, therefore SO must be also equal to x. Likewise, according to the same rule, in the same rectangle CGOF, side CF must be equal to the opposite side GO. But CF is x, therefore GO must be also equal to x. So we actually found out that quadrilateral CGOF is not a rectangle but a square, but because of the fact that all of its sides are equal to each other, each side of this square equals to x. Okay. In the next step, we will join points O and C together by straight line. Here we can implement rule 7. I'll repeat quickly on rule 7. According to rule 7, if a line segment that is drawn from the center of the circle bisects the chord, then it will be also perpendicular to that chord. So in the drawing we have a circle, point O is the center of the circle, and we have also line segment OM bisect chord AB. Why? Because of the fact that MA equals to MB. So line segment OM that is drawn from point O, that is the center of the circle, bisect chord AB. And therefore, according to this rule 7, whenever from the center of the circle you have a line segment that bisects the chord, it will be also perpendicular to that chord. That is to say, line segment OM is also perpendicular to AB. If OM is perpendicular to AB, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to this rule 7. So whenever you have a line segment that is drawn from the center of the circle and that line segment bisects any chord, it will be also perpendicular to that chord. Here, line segment OM that is drawn from point O, that is the center of the circle, bisects chord AB, and therefore line segment OM is also perpendicular to AB. That is to say, this angle equals to 90 degrees and this angle also equals to 90 degrees. So I can actually implement rule 7 in our drawing. Why? Because in our drawing we have here, if we relate to the quarter circle, in the quarter circle we have here chord ED, and we have also point O is the center of the quarter circle, and we have line segment OC that bisects chord ED. Why line segment OC bisects chord ED? Because of the fact that EC equals to CD. So we have line segment OC that bisects chord ED. Now we can implement here rule 7. Whenever you have a line segment that bisects the chord, it will be also perpendicular to that chord. That is to say, line segment OC that bisects chord ED will be also perpendicular to chord ED. That is to say, according to rule 7, line segment OC is also perpendicular to ED. If line segment OC is perpendicular to ED, it means that this angle equals to 90 degrees and this angle equals to 90 degrees. Again, if line segment OC is perpendicular to ED, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule 7. In the next step, we join points D and O together by a straight line. What is the definition of line segment OD? Line segment OD starts from point O, that is the center of this quarter circle, and ends at point D, that is the point on the quarter circle itself. So this is exactly the definition of a radius. Therefore, line segment OD is the radius of this quarter circle, and we know that the radius of this quarter circle equals to 5 units. AU equals to 5. Therefore, OD must be also equal to 5, because it is the radius of this quarter circle. So in the next step, we will implement the Pythagoras theorem on the right triangle CFO. So I'll copy the right triangle CFO in a new page and we'll implement the Pythagoras theorem on this right triangle, triangle CFO. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is the abbreviation for Pythagoras theorem. So actually, this is the right triangle CFO that I call it from the original drawing. According to the Pythagoras theorem, in this right triangle CFO, CO square equals to CF square plus FO square. So I write it down, CO square, that is the square of the hypotenuse, equals to CF square plus FO square. CO is the missing side, therefore we will leave it as it is, so it is CO square equals to CF square. CF equals to x, therefore CF square equals to x square plus FO square. FO also equals to x, therefore FO square equals to x square. So actually found out that CO square equals to x square plus x square, that is 2x square. CO square equals to 2x square. Here we take a root out of this equation and finally get that the missing hypotenuse CO is equals to the square root of 2 times x units in its length. So here this is CO is equals to the square root of 2 times x units in its length. In the next step, I'll copy the right green triangle COD in a new page, and we will implement the Pythagoras theorem on this right green triangle, triangle COD. Here by PT is the relation for Pythagoras theorem. The hypotenuse OD of the green right triangle COD equals to 5 units in its length. It is actually the radius of this quarter circle. And CD equals to x. So actually, this is the right green triangle COD that I call it from the original drawing. According to the Pythagoras theorem, in this right triangle COD, OD square equals to CD square plus CO square. So I write it down. OD square, that is the square of the hypotenuse, equals to CD square plus CO square. The hypotenuse OD equals to 5, therefore OD square is 5 square, that is 25. And it is equals to CD square. CD is x, therefore CD square is x square plus CO square. CO is equal to 2 times x, therefore CO square is equal to 2 times x squared, that is actually 2x squared. So in total, we actually found out that 25 equals to x squared plus 2x squared is 3x squared. Here we divide this equation by 3 and finally get that x squared equals to 25 over 3. Our mission is to find out the area of this semicircle. The area of any semicircle equals to the area of the circle over 2. And the radius of this semicircle is x, therefore the area of the circle is pi x squared, and the area of the semicircle will be pi x squared over 2. So the area of the semicircle equals to pi x squared over 2. So it is pi over 2, and x squared is 25 over 3. So we substitute x squared by 25 over 3. So in total we found out that the area of the semicircle equals to 25 pi over 2 times 3 is 6. So in total it is 25 pi over 6 square units. Or in terms of numbers, it is equals to 13.09 square units. So I repeat again, we should find out that the area of this semicircle equals to either 25 pi over 6 square units, or in terms of numbers, this equals to 13.09 square units. So in the next step, I will summarize the lecture. So in this lecture, we found out the area of this semicircle. In the drawing, we have a quarter circle, A or B is a quarter circle. Inside this quarter circle, we have this semicircle. And our mission is to find out the area of this semicircle. And in addition, we know that AO equals to 5 units in its length. AO is of course the radius of this quarter circle, and therefore we know that the radius of this quarter circle equals to 5 units in its length. So our mission is to find out the area of this semicircle. So first of all, we define the relevant points of this question with letters. We define the center of this semicircle, this point is point C. Likewise, we define the upper touching point of the semicircle and the quarter circle, this point is point D. We define the lower touching point of the semicircle with this quarter circle, this point is point E. Likewise, define the point of tendency of tangent BO with this semicircle, this point is point F, and finally we define the point of tendency of tangent AO with this semicircle, this point is point G. In the next step, we join points. First of all, we join points. We know that CE is of course the radius of this semicircle. CD is also the radius of this semicircle. Why? Because it starts from the center of this semicircle, that is to say from point C, and that's point D, that is the point of the semicircle itself. Therefore, CD equals to CE. They are both the radii of this semicircle. We define the radius of this semicircle as x. So CD equals to x, CE also equals to x. Likewise, we join points C and F together by a straight line. CF is of course the radius of this semicircle, that is equals to x according to our definition. Here we have the radius CF that is drawn to point F, that is the point of tendency of tangent BO with this semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent BO will be perpendicular to the radius FC. If BO is perpendicular to FC, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule 1, of course. Likewise, we join points C and G together by straight line. CG is of course the radius of this semicircle, that is equals to x according to our definition. Again, we have here the radius CG that is drawn to point G, that is the point of tendency of tangent AO with this semicircle. And whenever your radius is drawn to the point of tendency, then tangent AO will be perpendicular to the radius GC. If AO is perpendicular to GC, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to the same rule, rule 1. So by doing this construction, we create a quadrilateral CGOF. Inside this quadrilateral CGOF, we have 1, 2, 3 right angles. the sum of three right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral CGOF, we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be a rectangle if not a square. So we will relate to this quadrilateral CGOF as a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So a rectangle CGOF, side CG must be equal to the opposite side FO. But CG is x, therefore FO must be also equal to x. Likewise, according to the same rule, in the same rectangle CGOF, side CF must be equal to the opposite side GO. But CF is x, therefore GO must be also equal to x. So we actually found out that quadrilateral CGOF is not a rectangle but a square because of the fact that all of its sides are equal to each other. All the sides of this square is equal to x. So, in the next step, we join points O and C together by straight line. And here we can implement rule 7. I'll repeat quickly on rule 7. According to rule 7, if a line segment that is drawn from the center of the circle bisects the chord, then the line segment is also perpendicular to that chord. So in the drawing we have a circle. The center of this circle is here at point O. And we have also chord AB. And we have here line segment OM that bisects chord AB. That is to say, AM equals to MB. And because of the fact that line segment OM is drawn from the center of this circle, that is to say from point O, and it bisects chord AB, then this line segment OM will be also perpendicular to AB. That is to say, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to this rule, rule 7. Actually, we can implement rule 7 in our drawing. Why? Because in our drawing, if we relate to the quarter circle, we have the center of this quarter circle is here at point O. We have line segment OC that bisects chord DE. Why line segment OC bisects chord DE? Because of the fact that CD equals to CE. And because of the fact that line segment OC that is drawn from the center of this quarter circle bisects chord DE, it will be also perpendicular to chord DE. If OC is perpendicular to DE, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 7. Okay? So, in the next step, we implemented the Pythagoras theorem on this triangle CFO. So, I covered this triangle CFO in a new page and implemented the Pythagoras theorem on this right triangle, triangle CFO. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So actually, this is the right triangle CFO that I covered from the original drawing. According to the Pythagoras theorem, in this right triangle CFO, CO square equals to CF square plus FO square. CO is the missing side, so we leave it as it is, and it is equals to CF square. CF is x, therefore CF square is x square. Plus FO square. FO is x, therefore FO square is x square. So in total, we actually found out that CO square equals to x square plus x square. That is 2x square. So CO square equals to 2x square. We took a root out of this equation and found out that the hypotenuse CO equals to the square root of 2 times x units in its length. So this is CO that is equals to the square root of 2 times x units in its length. In the next step, I copied this right green triangle DCO in a new page and we implemented the Pythagoras theorem on this right green triangle DCO. So actually, this is the right green triangle DCO that I copied from the original drawing. We just right now found out that CO equals to the square root of 2 times x units in its length. DO, actually, we join points O and D together by straight line. Point O is the center of this quarter circle, point D is the point of the quarter circle itself. Therefore, or this, the radius of this quarter circle, that is equal to 5. CD equals to x. Again, this is the right triangle CDO that according to the original domain, according to the Pythagoras theorem, in this right triangle CDO, DO square equals to CD square plus CO square. Again, DO square equals to CD square plus CO square. DO is 5, therefore DO square is 5 square, that is 25, and it is equals to CD square. CD is x, therefore CD square is x square, plus CO square. CO is equal to 2 times x, therefore CO square is equal to 2 times x square, that is 2x square. So in total, we shall find out that 25 equals to x square plus 2x square. X square plus 2x square is 3x square, therefore we shall find out that 25 equals to 3x square. Here we divided this equation by 3 and finally found out that x square equals to 25 over 3. Our mission is to find out the area of this semicircle. The area of any semicircle equals to the area of the circle over 2. The radius of the semicircle is x, and therefore the area of the circle will be equal to pi x square, and the area of the semicircle will be equal to pi x square over 2. Repeat again, we shall find out that the area of the semicircle equals to pi x square over 2. X is of course the radius of the semicircle. So the area of the semicircle equals to pi x square over 2. But x square equals to 25 over 3. Therefore we can substitute x square in this equation by 25 over 3. We did it and actually found out that the area of the semicircle equals to pi over 2 times x square. And x square is 25 over 3. Substitute x square by 25 over 3. And in total we actually found out that the area of the semicircle equals to 25 pi over 2 times 3. 25 pi over 2 times 3. 2 times 3 is 6. So in total, the area of the semicircle equals to 25 pi over 6 square units. Or in terms of numbers, the area of the semicircle equals to 13.09 square units. Okay, again, we found out that the area of the semicircle equals to either 25 pi over 6 square units, or in terms of numbers, it is equals to 13.09 square units. Okay, thank you very much.